Hey guys, in this video we will implement an algorithm called Heaps algorithm in JavaScript. This is an algorithm that gives you all the permutations of any given collection of elements. Now if you're not mathematically inclined and didn't understand a word of what I just said, that's fine, as in this video we will go over all the mathematical concepts we need to first before we tackle this behemoth of an algorithm. By the way guys, my name is Justin and I'm currently a professional front-end developer based in Los Angeles. I make various coding videos ranging from algorithms like this one, making games with JavaScript, and tutorials in React. So if you guys like my content, please smash the like button and subscribe to my content to get more coding goodness. Anyways, on with the video. Let's first talk about what permutation is. Permutation of a collection of elements is a list of all possible ways you can order the elements. Let's use arrays to explain this concept. Suppose our collection was an array of 1 and 2. Then what are the different ways to order these elements? It's just 1, 2, and 2, 1. That is the permutation of this array. Now what about for 1, 2, 3? We can have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. As you can see, it's already getting harder to list all the possible permutations of a collection of 3 elements. Now, can you imagine doing this for 4 elements? What about an array even larger than that? This is what the Heaps algorithm gives you. For any given collection of elements, it will give you the list of all possible permutations. Pretty crazy, right? But before we go on to write the code for it, let's stick around the permutation concept a bit more. Remember the permutations for an array of 1 and 2? There were 2 different types of permutations, 1, 2, and 2, 1. For an array of 1, 2, and 3, there were 6 permutations if you still remember. As a matter of fact, can we come up with some type of a mathematical formula that will give us a number of permutations based on the number of elements? Right now we're not talking about the literal permutations, but rather just a number of permutations. In other words, given a collection of n elements, what are the number of permutations? Well, here's a pretty intuitive way to solve that. Suppose we are dealing with n equals 3. Meaning we have 3 elements. The elements can be arranged in 3 boxes. Now within the first box, how many different elements do we have to choose from? We can put 1 there, 2, or even 3. In other words, we have 3 choices within the first box, right? So now, having already put an element in the first box, how many elements do we have to choose from to put into the second box? We now only have 2. And finally, already having put the 2 elements in the first 2 boxes, we only have 1 choice left in the final box. You see these numbers, 3, 2, and 1? If you just multiply them, you get the total number of permutations for 3 elements. 3 times 2 times 1 is 6, which was the number of elements we had before. So this formula makes it easy for us to determine how many permutations there are for 4 elements. 4 times 3 is 12, 12 times 2 is 24, and 24 times 1 is still 24. So the total number of permutations is 24 for a collection of 4 elements. And as a matter of fact, here is the list of all 24 permutations. There's actually a mathematical way to denote this type of multiplying, where you start from a number, say n, and you keep on multiplying as you decrease the number by 1. It's called the factorial, and we can represent it with an exclamation mark. So 4 factorial is a shorthand way of writing this big thing right here. Anyways, now that we have a grasp of what a permutation is, let's go back to the Heaps algorithm. It was first proposed by a computer scientist named B.R. Heap in 1963. It was in a paper that he wrote. The way that it works, given an array, it just swaps 2 elements one at a time. It's not the only permutation algorithm in existence, but it has a time complexity of O to the n factorial, making a very efficient algorithm for permutations. So before we go on writing the algorithm in JavaScript, here are a few caveats. First of all, the algorithm is not at all intuitive. It is a highly complicated algorithm that about 99.99% of programmers would not be able to come up with just by sitting down and pondering about the code. That includes me, by the way. The proof of this theorem doesn't help much either, as it is proven in the original paper by a mathematical induction, which is a proof technique that we use in mathematics to prove theorems, but it doesn't really help us intuitively understand the code any better. I don't want to spend time in this video going over the proof, as most people watching will probably not understand how induction works anyways, and even if some did, the proof is also highly complicated and requires a lot of thinking and reasoning. The second caveat is this proof will use recursion. So if you're not comfortable with recursion, I highly recommend you practice some recursions and get a basic idea of how it works before you watch this video. And again, keep in mind that this is a complicated algorithm, so it is perfectly fine if you don't understand it. It's really one of those algorithms that you just gotta accept, so don't stress too much about it. Anyways, on with the code. All right, so I'm on my code editor here, and I'm on this random Wikipedia article on Heaps algorithm, and I'm gonna kind of implement what they have here, except using JavaScript and with a few different caveats. So let's first make a function. We'll call it const maybe get permutations. Permutations. It will accept an array, and we will use ES6 arrow notation for this one. Now, this is what we have to do. The first thing, this is my personal preference. The first thing is I want to make this a pure function. We're gonna be implementing a little bit. We're gonna have a bit more functions inside of this function that we're gonna use to solve this. But this function as a whole, I want this to be pure. Now, what I mean by that is we're gonna pass in an array. So let's say maybe someone will call it like get permutations and pass in 1, 2, 3, right? I don't want to manipulate the array that they pass us in. Meaning, if they like declared it before in the variable, const array is 1, 2, 3, and then they passed in the array here, array variable here instead, I don't want, if they were to console log after the array variable, I don't want that to change. Now, the reason why I say that is the nature of this heaps algorithm, it swaps the array in place. So we gotta somehow make it so that we don't manipulate the original array that we pass in. Yeah, so again, there's no real good reason why I want to do that other than the fact that I just like keeping my functions pure as much as possible. Now, again, keep in mind, I'm gonna declare functions inside here that are not pure. But this function, this get permutations function as a whole will be a pure function. And within here, now we have to make two different functions. One function that swaps an element. So let me just declare that right here. We will call this const swap. How about swap in place? So what it will do, it will get an array, and let's not call this parameter array because then we'll have a naming conflict with this outer array. So we'll call this R2 swap. How about that? We will be also given two indices. So maybe index A and index B. And the point of this array is it's supposed to swap within this R2 swap in place for index A and index B. So let's just use the traditional temp variable first. Store one of the values in the temp variable, R2 swap at index A, let's say. And then for R2 swap at index A, we will replace that with R2 swap index B. And finally, for R2 swap index B, we will set that equal to temp. So this will swap the array that we pass it for the index A and index B. Okay, and now we are gonna make a recursive function that's pretty much this that you see here in the Wikipedia article here. And if you look at this, they do have the swap function that they call here already. So that's the function that we just made right now. And again, this swap in place is not a pure function because it gets an array as a parameter and it swaps the array in place. So the array that you pass in will not always be the same array that you get back. But that's fine because this function as a whole will be a pure function, like I said. Now let's create this generate function that they call. And before we do that, let's do this. By the way, I forgot to mention, the output of this whole function as a whole will be an array of arrays. So for this 1, 2, 3 example, we will get back an array that has 1, 2, 3 as a first element maybe, and then 1, 3, 2, and pretty much it will list all the different permutations as an array. So that's the output of this function. So before we go on, let's declare a variable here called output. And we will initialize that as an empty array. And we will fill this in one by one with the permutations that we get from this crazy function that we see right here. Okay, now let's start, let's create this generate function here. So I'm gonna kind of follow their template. We're gonna call it const generate. It first takes in a number, integer, which is the length of the array, which we'll use later. And the next one is gonna be an array, but because we already have the R variable out here, I don't want any naming conflict, so let's call this heap R. So this will be an ES6 arrow function. And this is going to be a recursive function, so we always had to deal with the end case, right? For recursive functions. Let me just put semicolons here. Let's do if n is equals, triple equals to 1, then we want to add the heap array into this output. So we're going to do output.push heap array, except I want to make a new copy of this heap array. Because this heap array, we're going to constantly change it and manipulate it. So I want to just make a shallow copy of it and then put that in the output so that it won't get affected later. So the way that we do that is we could just duplicate it by calling the slice method on it. And that will give us a new copy of this array. And after that, we're just going to return because then we are done. But for the non-edge cases, not n equals 1. Not n equals 1, what do we want to do is we want to first call this recursively, reducing the n by 1, as you can see here. So we first generate, call it recursively, passing n minus 1 this time, and then heap array, like so. And after that, we are going to have a loop for let I equals 0. We're going to go, let I go till n minus 1. Again, n is from the generate function here, parameter here. And then I plus plus. And what do we want to do in this loop? So this is the part that really doesn't make sense. You just got to take its word for it. So if n mod 2 is equal to 0, what this means is if n is even, if the n that we have passed in here is even, we want to do something. Otherwise, if it's odd, we want to do something else. So what we want to do if it is even, we want to swap our array, calling our swap in place function. We're going to say swap in place heap array at index I and then n minus 1. That's when n is even. So this will swap heap array with these two indices, and our heap array after this function will be different. It will have these two elements swapped. Else, if it's odd, we want to swap in place again, except this time, heap array from 0, between 0 and n minus 1. So again, not at all intuitive. This is just how the function works. Let's see. And after we have swapped, still within the for loop, however, we want to do this. Generate n minus 1 and heap array. So we call it once here, and every time we're within the loop, we call it again. So this is a pretty crazy recursive function, and this generate function is pretty much done. However, we got to start using it now, right? So let's use it. Let's call it within our outer function, within our get permutations function. Let's call it out here. We will call it with the array that has been passed to this function, this R variable here. We will say generate. The first number is the length of the array, so we could just get that by r.length. And then we are going to, because we don't want to manipulate our array parameter that this function gets, because we want this function to be pure, we're going to pass it in, not the array itself, but the slice version, the copy version of it. That way we don't manipulate our original parameter. So this will call this whole generate recursive function, do all this stuff. For its edge cases, it will push to our output. And hopefully, now once this recursive function is all done, our output will have a list of all the different permutations. So at the very end, let's return the output. Now, if we have coded everything correctly, this should work. So this should give us an array of all the different permutations. Let's test it out. Let's try it out with the easy example. I'm going to console log the result of this, and let's call get permutations with just 1 and 2, a simple array. And we know what the answer is going to be, right? 1, 2, and 2, 1. Let's see if we get that. And we get 1, 2, and 2, 1. That's good. How about 1, 2, 3? A little bit more complicated. Do you remember our n factorial formula? We should get back 6 different permutations here. And 1, 2, 3, 4, 5, 6. We do get 6, and we get the different permutations. And finally, how about we try a little bit more complicated one? 1, 2, 3, 4. This should give us back how many? 4 times 3 is 12. 24. 24 different permutations. Let's see if we get that. All right, we got a whole bunch. I'm not going to count all this, but just take my word for it. This is correct. So this right here will give you all the permutations given in an array. This is called the Heaps algorithm in JavaScript. Now, I know what you're thinking. It's very not satisfying because it's very hard to get our mind around what this does. So what I want to do is I want to use 2 simple examples to go through this function with you guys. So I want to go through this function with these 2 examples here. I have my pages set up here, 1, 2, and 1, 2, 3. With these 2 examples, this is going to be very hard to follow. I might have been able to do this with like using good Photoshop and all that stuff, but my Photoshop skill's not there yet. So please bear with me with this pages example. Now, I highly recommend you guys pause this and try to do this on your own. Try to predict what the output is going to be, what this output array is going to be based upon these 2 examples without actually running the code yourself. Try to follow this along. So let's first try it with 1, 2. Okay, let's see. I'm going to use a little bit shortcut. I don't like writing all these commas and everything. So I'll just reference 1, 2 as 1, 2 and 1, 2, 3 as 1, 2, 3. So let's first call generate of 1, 2 as a length of 2, right? 2 comma and our array is 1, 2. So what does this do? If n equals 1, then push. But right now n does not equal 1. And right, by the way, our output is going to be here. And this one I'll make an array like so. So we call then generate n minus 1. Now n was 2, so we're going to call generate 1. Heap array didn't change at all, so it's still 1, 2. Now let's go back to up here, because now we're calling it with n equals 1 and 1, 2. So if n equals 1, which is the case, we want to push our array. So 1, 2 gets pushed in the beginning. Remember, keep in mind, this is an array. And then we just return. So we go back, this case is done. We go back to this case, except we have passed this line and now we are within the for loop. Let I equal 0, I is less than 2 minus 1, which is 1. So we just iterate this for loop once, which is good. Hallelujah, thank God. N was 2. If it is even, which it is in this case, we want to swap between 0, we're in the iteration 0, 0 and 2 minus 1, which is 1. So swap 1, 2 becomes 2, 1, right? We have swapped them in place. And then after we have swapped, we call generate with 2 minus 1, which is 1, 1 for 2, 1. So we call it generate 1 for 2, 1. Now we go back here because we're calling it with 1, 2, 1. If n equals 1, which is the case, we push. We push like so, and then we return. So we're done. We go back to g equals this case, except array is 2, 1 this time. But we're done with this for loop here. So we come out, and now we're done with the function, and our output has correctly been established here. Again, I know that was very hard to follow. Just please try to do this on your own first. Now, let's try to do it with the 1, 2, 3 example. So we will call, by the way, our output is here. Freaking pages. Okay, it's because I don't have Word. All right, but anyways, let's call generate of 3, length is 3, and then 1, 2, 3, right? So if n equals 1, nope. We're gonna call generate of 2, 1, 2, 3, right? So now let's go into this function. If n equals 1, nope. Generate 1 of 1, 2, 3. If n equals 1, yup. We're going to push our array, which is 1, 2, 3 right now. And we're done with this example. We go back to this one. We have passed this line, however. We go inside this crazy for loop here. For let I is 0, 0 is less than n minus 1. So just that's 2 minus 1. So that's 1. So we just go through this for loop once because we're starting from 0 where I is less than 1. So we just go through it once again. Okay, if n, which is even, okay, so we're in here, we swap 0 and 1. So 0 and 1, we swap these. So 1, 2, 3 becomes 2, 1, 3. And then we call this again. So now we are calling G1 of 2, 1, 3 this time. If n equals 1, yep, we push it. So we push, we get 2, 1, 3, and then we are done with that iteration here. Now we have called this. Remember what we said? We just ran this once, so we're done with this iteration here too. Here. But keep in mind that our array is now 2, 1, 3. So we're back to here, our original function call. But we have passed this line, this generate, our first generate call with n equals 3. Now we do this loop. For I is 0, less than 2, so 0, 1, we go through this for loop twice. Remember that, we gotta go through it twice. N is 3, so it's odd, so we swap between 0th index and the second index, 3 minus 1, which is second index. So 0th index and the second index is 2 and 3. So 2, 1, 3 now becomes, what? What did I say? Last one and the first one, 0th one, right? 3, 1, 2, I believe. And then we call generate 2 of 3, 1, 2 now. So we go back up here. We generate the 1 version of that, of 3, 1, 2. And that's n equals 1. So we push here. Man, I really hope I'm doing this correctly. And we are done with the iteration. So we're back on 2, 3, 1, 2. We go through this loop once, remember. N is even, so we swap between 0 and 1. So 3, 1, 2 becomes 0 and 1, 1, 3, 2. And then we call the 1 again, g of 1 at 1, 3, 2 now. If n equals 1, yes it is, so we push 1, 3, 2 here, and we're done with that iteration. And we go back to our g of 2, but we only go to this loop once, so we're done with this g of 2. Now we are back at this freaking g of 3, which we have finished our first iteration. So we go to our second iteration where I is 1. This is our last iteration. N is odd still, remember. So we go through here, we flip 0 and 2. So 1, 3, 2 becomes 0 and 2. These two flip, 2, 3, 1. And then we call this function again, g at 2 of 2, 3, 1 this time. Go out here, call g of 1, 2, 3, 1. And then if n equals 1, yes it is, we push it to our output. And then this is done. We iterate it once. What happens here? We go through this for loop once. If n is even, which is in this case 0 and 1, we flip this one and that one. So 2, 3, 1 becomes 3, 2, 1. And then we call the function with g equals n equals 1 this time. And if n equals 1, we push. Yes. Oh my god. Okay, so we're done with that one. G2 is also done. This one's done. Now we're back at our original function call. We have finished our second 2 iterations that we had to do for this for loop, and we are finally done with this function, and our output has been established. Now, let's see if we get the correct order. It should be in this order. If we follow the directions, when we call this function, it should give us the same order that we have here. Let's run the code. 1, 2, 3, 2, 1, 3, 3, 1, 2, 1, 3, 2, 2, 3, 1, 3, 2, 1. Now, so that's good, I'm not gonna do this for 4 elements because that's just gonna be way too crazy to keep track of. However, hopefully you guys get the gist of how things get swapped around in each iteration. Anyways, guys, that was Heaps algorithm in JavaScript. Hope you guys like this. If you guys want a copy of this code right here, I will post in the links description below the gist of this on GitHub. So you could just find a link to that in the description below. And by the way, like I said, this is not the only algorithm that gives you all the different permutations. I'm on the Wikipedia article right now. There is also this one called Steinhaus-Johnson-Trotter algorithm. That's another algorithm that gives you all the list of permutations. So if you are a mathematical nerd like me, then maybe you could check this one out too. Maybe I'll make a video for it, but who knows. By the way, the purpose, my motivation for making this video was because of free code camp. So for those that don't know, I've been going through all of the free code camp's algorithm videos, and the one that was coming up for me is called this one. It's under the coding interview prep, under the algorithm section, and it's called the no repeats please. So this one actually required an algorithm like this. So instead of putting this tutorial about this Heaps algorithm inside this tutorial video for this no repeats please algorithm, I decided to make a separate video for Heaps algorithm. And once I do this free code camp tutorial, I'll reference this video here. So for those guys who is watching this video first, try this now. With the algorithm that we made, with the function that we have just created, try to solve this algorithm here on free code camp. Trust me, it will be a lot easier with this function that we have here. So anyways, guys, that was my content. This was about the Heaps algorithms. If you guys like my content, please click like and subscribe to my content for more coding goodness. And I will see you guys next time.